Students, all of you, good evening. Welcome to the session. Continuation of circuit theory, that is network theory concepts. With respect to chapter 1, that is fundamentals of electrical circuits. I'm starting lecture 10. In the previous session that I discussed about what the concept of KCL and some practice questions with respect to KCL, and what the concept of KVL and some practice questions with respect to KVL that I given. Before starting the next topic, you have to solve 2 more questions based on KVL and 2 or 3 questions based on how to calculate the number of branches, number of nodes, KCL equations and KVL equations. And after that, we go for what are the equivalent resistance in series connection, equivalent inductance in series connection, equivalent capacitance in series connection. Similarly, resistance, inductance, and capacitance equivalents in parallel connection. After that, you have to see what are the different types of sources. Students, can you try this problem? This one important model. For the circuit shown in figure, shown in figure, determine the voltage as V1, V2, and E. So this is the given circuit. This is one source, and this also on battery voltage. That is given is V1. This battery voltage is 2 volts, and this battery voltage is 4 volts, and this point is grounded. This is grounded. This is grounded. Then this voltage is E. This is E, and this voltage is 6 volts. This is given is 6 volts, and this is 8 volts. 8 volts, and this is V2, and this is 10 volts. Then you have to calculate V1, V2, and E. Then how to calculate, students? Right? Can you apply KVL here? Right? That this is 1. How to apply KVL here? This is KVL 2. I'm applying KVL 1. Students, how to take sign convention? I'll let explain in the discussion of KVL. This is V1, positive to negative, negative, -2, negative to positive, positive plus 4. This is ground potential, this is grounded, ground equal to 0 potential. Then from this, what is V1 equal to, friends? -2 volts. Okay. This is a calculation of E. Can you apply KVL 2? Right? KVL 2. If you apply KVL here, this is V2, this is V2. Then V2, negative to positive, positive, plus 6. V2 plus 6. Positive to negative, negative, -8 equal to 10. Then how much V2 you can get? V2 equal to 10 plus 2. This is equal to 12 volts. That is V2 equal to 12 volts. Now you have to calculate E. To calculate E, apply like this or like this. How to apply KVL? I'm applying KVL here. This is KVL. This is KVL 3. If you apply KVL, yes, starting 0, positive to negative, negative, -4, positive to negative, negative, -8, positive to negative, negative, -8 equal to 10. Equal to 10. Then from this, -E, -12 equal to 10. Then what is E equal to? -12 minus 10. This you bring this side, minus E this side, -22 volts. C equal to -20. Like this you have to calculate. Yeah, this important model, 5-star model. Just you concentrate how you are applying KVL for this type of problem. See, one more problem that I'm explaining here, one more example, students, that you have to concentrate. For example, if the circuit is given like this, let this given is 1 volt, and this resistance is 1 ohm, so 1 ohm resistance, and this also 1 ohm resistance, 1 ohm resistance, and this is 1 volt, this is 1 volt, and this also 1 ohm resistance, 1 ohm resistance, and this also 1 ohm. This battery voltage is minus plus 1 volt, like this it is given. This point is V2, this point is V1. Then you have to calculate. Then these are the options it is given, friends. V2 equal to 1 plus V1. Option B, V1 equal to 1 plus V2, 1 plus V2. V1 equal to V2, V1 equal to V2 minus 1. So V1 equal to V2 minus 1. Is V2 equal to V1 plus 1 or V2? So V1 equal to 2V2. Then which option is correct? Can you try this? Yes, I'm taking the, let this is the current direction. The current direction is positive to negative I taken. Positive, let this is I1 current. In this loop also there is a current positive to negative. Let this current is I2. Current is I2. Now apply KVL here, friends. If you apply KVL here, what you get? Positive, negative, positive, negative, minus I1, minus I1, negative, positive, plus 1, equal to 0. Then 2I1 equal to 1. What is I1 equal to 0.5? 0.5 amps. I1 equal to 0.5 amps. Then can you try KVL here? Apply KVL in this loop. So it's negative to positive, plus minus, plus minus. This is minus I2. This also minus I2 equal to 0. Then from this 2I2 equal to 1. What is I2 equal to 0.5? But you have to find what the relation between V1 and V2. To find the relation between V1 and V2, then apply KVL here. To find the relation between V1 and V2, then apply KVL here. Then what you can get, friends? This is V1. I'm applying KVL here. V1, positive to negative. Positive to negative means minus I1. Negative to positive. Negative to positive. Plus 1. This is minus I1 into 1, sir. Minus positive to negative. This polarity. But this I1 into 1 minus I1. That is current into resistance gives the voltage. This is plus 1. Next. Negative to positive. This negative, this is positive. Negative to already polarity we given. Negative to positive plus I2. I2 into 1 I2 is equal to V2. Is equal to V2. V1 minus 0.5 plus 1 plus 0.5 equal to V2. Thus I1, I2 already calculated. I1 is 0.5, I2 is also 0.5. Minus 0.5 plus 0.5 cancel. What is V2 equal to? This is V1, this is 1. V2 equal to 1 plus V1. V2 equal to 1 plus V. That is option A is the right answer. Like this, you have to proceed. This is one more model. Here, first I apply this KVL. Apply the KVL here. Then I take it like this. You take any direction. Follow the one, in one loop, you follow the one direction. Like this or like this. Any direction you have to follow. Yes, friends. Here is the one model of calculation. Remaining using KVL, KCL, combination of nodal analysis, mesh analysis. By combinedly, we can see later on. Because if you have to solve the problems using nodal analysis and mesh analysis, you have the minimum basic knowledge on the KVL and KCL. In some models of question directly we can apply KVL. In some models of questions KCL. In some other models nodal analysis, mesh analysis. These basics are required. Combinedly how to solve the questions later on we will see. After completing the equivalence in series connection, parallel connection. Here, this is one circuit it is given strength. This is L. This is R1. This is R2. And this is R3. This is V. Can anybody tell how many number of nodes are there in this circuit? How many nodes are there? How many number of nodes are there? This is one node. This is the one simple node. This is also one simple node. And this is one principal node. One principal node. And this is, what about this? Only two branches now. This is the one principal node. This is one principal. Here there is a capacitor. Is there? Is correct? Here there is a capacitor. Okay. And this is one simple node. Because two elements are connected. Two elements are connected. Simple. Here three elements are connected. 1, 2, 3. Then there's a principal. This one more principal node. 1, 2, 3 branches are connected. One more principal. That is NP. Then how many simple nodes are there? Only two branches are connected. Simple node. Greater than two branches are connected at a node. Then it is a principal. Then there is a principal. How many simple nodes are there? 1, 2, 3 simple nodes. How many principal nodes are there? 1, 2. Total how many nodes? The total number of nodes equal to 5. How many number of branches, friends? Branches. This is 1, 2, 3, 4, 5, 6. 6 branches. How many number of loops? How many number of loops, friends? Okay, this is one loop. This also one loop. The number of loops you have to find. And this also loop. This also loop. The total number of loops equal to 3. How many number of principal nodes? Principal nodes are 1, 2. 2 principal nodes. How many number of simple nodes? How many number of simple nodes, sir? 3 simple nodes. How many number of KVL equations? I already told how to calculate KVL equations. P minus n plus 1. P minus n plus 1. The KVL equations are given by, that is P minus n plus 1. How many number of branches? 6. Nodes 5 plus 1. That equal to, number of KVL equations are 2. How many number of KCL equations? KCL equations equal to NP minus 1 form. Number of principal nodes minus 1. That is the KCL equation. How many number of principal nodes, friends? The principal nodes equal to 2. That is 2 minus 1, 1. One KCL equation is required. But how many number of KVL equations are required? 2 KVL equations are required. Like this you have to calculate. Can you try this? Come on, do it, friends. How many number of nodes? How many number of simple nodes? Number of principal nodes? Number of branches? Number of meshes? Number of KCL equations? Number of KVL equations? Come on, do this. Yes, friends. Here three branches are connected. 1, 2, 3. One principal node. One principal node. Here two branches are connected. This is one branch. This is one branch. This is one simple node. Here also two branches are connected. Now this is also one simple node. Here three branches are connected. Now how many three branches are? Sorry. Here how many branches are connected? Can anybody tell? Is it two branches or three branches? Here how many branches are connected? Three branches or two branches? Here there is no. This is the open circuit. Open circuit means there is no meaning of this branch. How many? This is a simple node. Two branches. It is a simple node. And here also it is a open circuit. Here also it is a open circuit. Now how many branches are connected? Two branches. This also one simple node. Simple node. Two branches are connected. It is a simple node. Then this here three branches. This is one principal node. One principal. One principal. This is NS1, NS2, NS3. And here this is the source. Now source is one branch. This element is also one branch. This is one node. This is one. There is NS1, NS2, NS3, NS4, NS5. That is also one simple. Total how many nodes, friends? Total how many nodes? This is one branch. This is one branch connected here now. That is also one simple. Clear? Now total how many nodes? 5 simple nodes, 2 principal nodes. Number of nodes equal to 7 students. How many number of branches? Can you calculate how many number of branches are there? Come on, students. The number of branches. This is 1. This is 2. This is 3. The number of branches. How many number of branches are there? First, number of simple nodes. Number of simple nodes is 5. Number of principal nodes are 2. Now calculate number of branches. Now calculate number of branches. 1, 2, 3, 4, 5, 6, 7, 8. Here there is no current is passing through these branches. If you want, once again, I'm counting this number of branches. How many number of branches? Come on, do it. Count this. The number of branches equal to, this is 1. How many number of branches? This is 1. This is 2. This is 3. This is 4. This is 5. This is 6. This is 7. This is 8. The number of branches equal to 8. How many number of meshes? How to calculate the number of meshes? Number of meshes, that is equal to number of independent loops. P minus n plus 1. 8 minus, this is the number of branches. Number of nodes is 7 plus 1. 8 minus 7 plus 1 students. The number of meshes equal to, how many number of meshes here? This is equal to 2. The number of meshes equal to 2 students. Number of KCL equations. What is the formula for number of KCL equations? NP minus 1. Number of principal nodes minus 1. That is 2 minus 1, 1. How many number of KVL equations? Number of KVL equations equal to number of meshes. P minus N plus 1. This is equal to 2. Number of KCL equations is, yes, number of KVL equations is B minus N plus 1. That is correct. That is 2. Is it correct? Any doubt? Clear, friends? That you have to concentrate. Next. Here is the gate PYQs. Can anybody answer this question? Come on, do it. The minimum number of equations required to solve the below circuit is. The minimum number of equations required to solve the below equation is. First, you tell me how many number of nodes. Here it is not asked is a KCL or KVL. You calculate the KCL equations, you calculate the KVL equations. Calculate the KCL and KVL equations, which are the minimum, that is the minimum number of equations. Try it, students. Just I'm giving 1 minute of time. Yes, any answer? Nobody responding. Can anybody tell how many number of nodes are? Number of nodes. How many number of nodes? Yes. This is one principal node, and this is this one branch, this one branch. This one simple node, one simple node. This total is one node. This one principal node, and this also 3 branches are connected. Now this is one principal node, and this also one principal node, NP4, and this also one principal node. This also one principal node, NP5. Simple nodes are how many simple nodes? One simple node. Total number of nodes equal to 6 nodes. Total number of nodes equal to 6. How many number of branches? Number of branches. The number of branches equal to this 1, 2, 3, 4, 5, 6, 7. This 8. How many number of branches? 9. Total number of branches equal to 9. This, then number of KVL equations. What is the formula? Number of KVL equations equal to P minus N plus 1. P minus N plus 1. The number of branches are 9. Nodes are 6 plus 1. 9 minus 6, 3, 3 plus 1, 4. Number of KCL equations. Number of KCL equations are number of principal nodes minus 1. How many number of principal nodes? 5. 5 minus 1. This is equal to number of KVL equations. I'm getting 4. Number of KCL equations also I'm getting 4. That's why take any one. The minimum number of equations equal to 4. The minimum number of equations are required to solve this below circuit is 4 equations. KVL equations also 4 is required. KCL equations also 4 is required. Clear, friends? Like this, we have to calculate. Yeah, this is one branch. Source is one branch. Resistor is one branch. 2 branches are connected, simple node. Greater than 2 branches are connected, principal nodes. Okay, that you have to consider. Yeah, this how to calculate number of KCL equations, KVL equations, number of branches. Okay, number of nodes, how to you have to calculate. Yeah, all these that you have to consider. This is one concept, and what the KCL, what the KVL, all these concepts that experts. With this knowledge, now I'm moving to one more important concept, that is series and parallel connections, voltage division and current division. This is very, very important, friends, that you have to concentrate. Series and series and parallel connections, parallel connections, and voltage division, how to apply voltage division rule in series connection, voltage division and current division rules, current division rules, series and parallel connections, comma, voltage division and current division rules. First, we have to see that is the series connection of resistors. How to apply the series connection of the resistance. Series connection of resistance. Series connection of resistances. Let's consider, all of you well known this topic. Let's consider two number of resistors are connected in series. Let's consider two number of resistors. First, I am taking the two resistors. Two number of resistors are connected in series. This is R1 and this is R2. Let the total voltage is V. The current is I. Let the voltage across R1 is, that is V1. Voltage across R2 is V. That is, in series connection, one observation is what the current is passing through R1, same current is passing through R2. That is, any number of elements you have to connect in series, friends. In series connection, current is constant. That is first observation. In series connection, current is constant. Current is constant. Every observation is. Then what that current I equal to? Is I equal to V by the total resistance R1 plus R. Is I equal to V by R1 plus, or otherwise, how to write like this before this. In series connection, current is constant. Okay. And voltage is divided. But voltage is divided. In series connection, current is constant, voltage is divided. Then by using KVL, if you apply KVL here, using KVL, then we can get V equal to V1 plus V. We have to get V equal to V1 plus V using KVL. To try to apply KVL here, how to apply KVL that you know. This is plus, this is minus. Then V equal to V1 plus V. Then from this, how we can write, friends? This V equal to V1, I am writing I into R1. This current is constant now. This I into R1. V2, I am writing I into R. Then V equal, take I is common, R1 plus R2. Then V by equal to R1 plus R. This is equal to R equivalent. From this, what is I equal to? V by R1 plus R. Then what is the R equivalent? The R equivalent equal to R1 plus R. That is, if two resistors are connected in series, the resultant equivalent resistance equal to sum of the two resistances. The resultant equivalent resistance equal to sum of the two resistances. Now, if you have to calculate V1 in terms of resistances and V2 also in terms of resistances, one method is like this, you have to calculate. What is V1 equal to I into R1? What is I? V by R1 plus R into R1. That is V1 equal to V into R1 by R. This is called voltage division rule. V1 equal to V into R1 by R1 plus R. What is V2 equal to, sir? I into R2. What is I? V by R1 plus R into R. That is V2 equal to V into R2 by R1 plus R. If two number of resistors are present, like this, or otherwise simply you can do like this using voltage division rule. If you want V1, if you have to calculate V1, V1 equal to total voltage into this resistance by total resistance. V2 equal to total voltage into this resistance by total. This is called voltage division rule. Voltage division rule or voltage divider rule. How the voltage is divided? That is V1 equal to V into R1 by R1 plus R. V2 equal to, that means simply remember like this. No need to do all these calculations. I value all these. For example, let this is R1, this is R2. I am applying the total voltage is V. Now you have to calculate V1 and V2. You have to calculate V1 and V2. Then can you tell what is V1 equal to? This voltage into V1 is voltage across this resistance now. V in same resistance by total resistance. Can you tell what is V2 equal to? This V2 if you want, total voltage into that resistance by total resistance. R1 plus. Yeah, this is the calculation of V1 and V2. That is according to voltage division rule. If two resistors are connected, like this. If two equal resistors are connected, if two equal resistors are connected in series, if two equal resistors are connected in series, connected in series. If two equal resistors are connected in series, this is R, this is also R. If two unequal resistances are there, R1 plus R2. Here also same, this is R, this is R. Then what is R equivalent? R equivalent equal to 2R. R plus R, this is equal to 2R. If two equal resistances are connected in series, R equivalent equal to 2R. That is R plus R. How we are getting this 2R? Adding these two resistors. That is R plus R. This is equal to 2R. For example, if n resistors are connected in series, if n resistors are connected in series, if n resistors are connected in series, let this is R1, R2, R3, and so on, Rn. So this is R1, this is R2, this is R3, and so on. That this voltage is V1, this voltage is V2, this voltage is V3, and so on. This voltage is V2. Now, what is R equivalent? Is R equivalent equal to R1 plus R2 plus R3 plus and so on. Even voltage also V equal to V1 plus V2 plus V3 plus and so on. But the current remains constant. In any resistor, the current remains constant. If you have to calculate what is the voltage across nth resistor, what is the voltage across nth resistor? If you have to calculate voltage across the nth resistor equal to Vn equal to total voltage that we are applying, the total voltage is V. That we are applying this total voltage is V. If you have to calculate voltage across nth resistor, V into that resistance by V into Rn by R1 plus R2 plus and so on Rn. R1 plus R2 plus and so on R. Okay, like this you have to apply the formula. R1 plus R2 plus and so on. Yeah, this is voltage across the nth resistor. If you have to calculate voltage across the second resistor, V2 equal to V into R. Third resistor, V3 equal to V into R. Like this you have to apply the formula. But if n equal resistors are connected in series, if n equal resistors are connected in series, if n equal resistors are connected in series, are connected in series, if n equal resistors are connected in series, what is R equivalent equal to? Is R plus and so on n resistors. Then what is R equivalent, students? NR. Very important. If n equal resistors are connected in series, the equivalent resistance equal to n times of R, n into R. If three equal resistors are connected, 3R. If five equal resistors are connected, 5R. Seven equal resistors are connected, 7R. Like that you have to solve. Next, I have to calculate series connection of inductance and capacitance. You have to calculate series connection of inductance and capacitance. Apply series connection of inductors and series connection of capacitors. Actually, to explain the series connection of inductors and capacitors, you have to take the concept of impedance. Uh, Actually, for resistors also you can explain from the impedance, but here no need to take that impedance. Directly I take an R. To explain this, let's consider impedance. Let's consider in detail about impedance. All these you will see in the AC analysis, but up to now you remember. Let's consider impedance. For example, two impedances are connected in series. Let this is Z1, this is Z2, this is Z2. These two are connected in series. Let this is V plus minus. The voltage is divided. This is V1 and this is V2. At this current in series connection, current remains constant. In series, current is constant. In series connection, current is constant. Current is constant. Current is constant. Then according to KVL, V equal to V1 plus V2. Then V equal to, what is V1? I into Z. What is V2? I into Z. Then what is V by equal to? How to write? V by equal to Z1 plus Z. V by equal to Z1 plus Z. This is equal to Z equivalent. This is equal to Z equivalent. Therefore, what is the in series connection? Z equivalent equal to Z1 plus Z. Z equivalent equal to Z1 plus Z. For n impedances, if n impedances are connected in series, what is Z equivalent equal to, friends? Z1 plus, Z2 plus, and so on plus Z. Similarly, if you have to calculate V1, V1 equal to I into Z1. This is equal to, from this, what is I equal to? V by Z1 plus Z. Then substitute I value here, V into Z1 by Z1 plus Z. This is called voltage divider for impedances. Similarly, what is V2? V2 equal to I into Z2. Substitute this I value here, sir. That is V into Z2 by Z1. Or simply, this voltage in, if you want V1, V1 equal to voltage divider rule, sir. V1 equal V into Z1 by Z. V2 equal V into Z2 by Z1 plus Z. Okay, this is V2. Okay, this is called voltage divider rule. Voltage divider. That is, current is constant, but voltage is divided. Voltage is divided. Now, these formulas I have to apply for inductance and capacitance. For inductance in series. Inductances are inductance in series, or series connection of the inductors. First, I have to explain series connection of inductors. Connection of inductors. For inductance, simply you have to take what is impedance equal to J XL. The impedance equal to J omega L. Inductance impedance equal to J omega L. How to take? That is inductance equal to J omega L. Now, I am applying Z equivalent equal to Z1 plus Z2. This is, if inductances are in series, let two inductance I take. This is J omega L1, or simply how to take the L1. Inductance is L1. Inductance is L2. Connected in series. This is V plus minus. This voltage V1, this voltage V2. Replacing Z equal J omega, that is J omega L equivalent equal to J omega L1 plus J omega L2. Take J omega is common, then L equivalent equal to L1 plus L2. Simply you can get like this. This is the concept. To explain this, I am taking the impedance concept. L equivalent equal to L1 plus L2. If two equal inductances are connected in series, before that, apply voltage divider rule. V1 equal to V into Z1 by Z1 plus Z. Replace this. V into Z1 is J omega L1 by, that is J omega L1 plus Z2 is J omega L2. J omega cancel. V into L1 by L1 plus L2. Directly take V1 if you want, V into L1 by L1 plus L2. L1 by L1 plus L2. This is V1. Similarly, what is V2? V2 equal to V into, if you want, write once again formula that V into Z2 by Z1 plus Z2. V into Z2 by Z1 plus Z2. Replace Z2 is J omega L2. This J omega L1 plus J omega L. Take J omega is common. That is V into L2 by L1 plus L2. That is V2 equal to V into L2 by, you take, if you have to calculate voltage across L2, take that inductance to total inductance. Yes, friends. Again, no need to write impedance. Just to give the proof only, I taken the impedances. Directly you take inductances. That is V. If they given impedance, then only you take impedance. If inductances are given, directly you have to take the inductances. That is V into L1 by L1 plus L2, V into L2. If there is a two inductances are connected, if two equal inductances are connected in series, then how we can write? If two equal inductances if two equal inductances connected in series, connected in series, connected in series, then what is L equivalent equal to? 2L, 2L, similar to resistor. The inductance equivalent is similar to resistor. Simply remember like if n inductances are connected in series, n inductances connected in series, connected in series, that is this is L1, this is L2, and so on Ln. Whatever the number of inductance you have to connect in series, the current remains constant, but voltage only divides. The series connection of inductances are similar to, the concept is similar to resistors. Then what is L equivalent? L1 plus, L2 plus, and so on plus Ln. Directly have to add the inductances. Then if you have to calculate voltage across the nth inductor, voltage across nth inductor if you have to calculate, then Vn equals friends, total voltage into Ln by L1 plus, L2 plus, and so on. Like this you have to. It's Vn similar to resistors. If n equal inductors are connected in series, if n equal resistors, sorry, if n equal inductors, sorry, if n equal inductors are connected in series, inductors or inductance connected in series, when equal inductance are connected in series, connected in series, then what is L equivalent? N times of L. L equivalent equal to n times of. Yeah, this is series connection of the inductors. And what is series connection of the capacitors? I'm adding the slides just. Next, what is the series connection of capacitors? Series connection of capacitors. For capacitance, you have to take Z equal to 1 by j omega. Then what is the Z equivalent, friends? For example, two capacitors are connected in series. Let's consider two capacitors are connected in series. Let this total voltage is plus minus. Total voltage is V. Let this is C1, this is C2. Then you take impedance Z equivalent equal to Z1 plus Z. 1 by j omega C equivalent. In terms of impedance in terms of capacitance, that happens 1 by j omega C. 1 by j omega C. J omega cancel. 1 by C equivalent equal to 1 by C1 plus 1 by C2. You can also write like this: C equivalent equal to C1 C2 by C1. Exactly opposite. That is for capacitors different formula. In inductors and resistors, if it is a series, directly added. But in capacitor, series connection is different. This is very good. C equivalent equal to C1 C2 by C1 plus C2. Clear. Now, how to calculate V1? V1 equal to V into Z1 by Z1 plus Z. How to apply? V into 1 by j omega C1 by 1 by j omega C1 plus 1 by j omega C. If you simplify this, V into 1 by C1 by 1 by C1 plus 1 by C. Take j 1 by j omega is common, that will be cancelled. Then V into 1 by C1 by C1 plus C2 by C1 into C. That is V into 1 by C1 into, this goes to numerator, C1 into C2 by C1 plus C2. This C1 C1 cancels. What is V1 equal to? V into C, very important. C1 plus C. That is in inductor and resistor voltage divider rule. In resistor and inductor voltage divider rule, If you want V1, you take an R1. If you want V1, you take an L1. But here in capacitors, if you have to calculate voltage across C1, this is V1, this is V2. If you have to calculate voltage across C1, don't take C1, you take C2. That is V into C2 by C1. Opposite capacitance you have to take. Don't take same capacitance. Another capacitance, not opposite. Another capacitance you have to take. V into C2 by C1 plus C2. Then what is V2 students? V2 equal direct. Similarly, I'm writing similarly. Same procedure you have to apply. Like this only you have to derive. Similarly, what is V2? V2 equal V into C1 by C1 plus C2. This is V2 calculation. Capacitor series connection is different as compared to resistor and inductor. Resistor inductor concept series connection concept is same, but capacitor is different. That is if two equal capacitances are connected in series, if two equal capacitors connected in series, if two equal capacitance is connected in series, then what you have to write? C equivalent equal to C by 2. It's not 2C, it is a C by 2. That is because C1, C2 by C1 plus C2, that is C by 2. If n capacitors are connected, connected in series, then we have to write like this. If n capacitors are connected in series, that 1 by C equivalent equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus and so on plus 1 by Cs. Like this you have to calculate. 1 by C equivalent equal to 1 by C1 plus 1 by C2 plus. If n equal capacitance connected in series, before this, here I given n capacitances are connected in series like this. C1, C2, C3, C1, C2, C3, and so on, Cn. That this voltage is V1, this voltage is V2, this voltage is V3, this voltage is V3. Then in this case, capacitor series connection, if n capacitors are there, then how to calculate the voltage? Voltage across nth capacitor equal to V into 1 by Cn by, important formula, 1 by C1 plus 1 by C2 plus and so on. Very important formula. Not V into Cn, V into 1 by Cn. Because impedance is V into Zn, V into Zn. But Zn is 1 by j omega c. That's why Vn equal to, because impedance is 1 by j omega c. Because of that reason only we are getting like this. V into 1 by Cn by 1 by C1 plus 1 by C2 plus and so on. This voltage. See, I given for two capacitors. How to calculate directly? More than two capacitors are given. Follow this formula. V into 1 by Cn by 1 by C1 plus 1 by C2 plus. Clear, friends? If n equal capacitors are connected in series, what are the equivalent? If n equal capacitors, are connected in series, then what is the C equivalent? C equivalent equal to, in series connection, resistors and inductance n times of R, n times of L. But in in series connection of capacitor, not parallel connection, in series connection of capacitors, it is not n times. This 1 by n. C equivalent equal to C by n. Two capacitors C by 2, n capacitors C by n. That is, in resistors and inductors in series connection, n times. But here 1 by n times. N times 1 by n times C equivalent. C by n. Okay, this is about the series connection of the resistors, inductors, and capacitors. Resistors, inductors concept is same, but series connection of capacitor is opposite to the resistor and inductors. Next one is parallel connection. Actually, how to see parallel connection of resistors. In parallel connection, In parallel connection, voltages are equal, but currents are divided. Voltages are equal, but currents are divided. That's why currents are divided. That's why in parallel connection, we have to apply current division. Currents are divided. It's not equal. Currents are not equal. First, we have to see parallel connection of resistors. That is parallel connection of resistors. In parallel connection of resistors, let's consider two resistors are connected in parallel. Let's consider two resistors are connected in parallel. Let this is R1 and this is R. Voltages are equal here. This is V. Let this current is I. This current is I1. This current is I2. That is in parallel connection. But the voltage across R1 equal to voltage across R2 equal to V source. Voltages are equal. Voltage across R1 equal to voltage across R2, that equal to V. But what the total entering current equal to sum of the two currents, I equal to I1 plus I2. That is currents are divided, voltages are. Shall I write I equal to, according to Ohm's law, I1 equal to, the voltage at this point is V, voltage at this point is also V. That is V by R1. I2 equal to V by R. V by R. How to bring this V this side? I by V equal to 1 by R1 plus 1 by R. I am taking V is common. That is 1 by R1, 1 by R2. Shall I write like this? R1 plus R2 by R1 into R. Then I by V is R1 plus R2 by R1. But V by I want. What is V by? Exactly reverse. I by V is this one. V by is R1 R2 by R1 plus R. Okay, this is equivalent to R equivalent. That is R equivalent equal to R1 R2 by R1 plus R. Just like capacitor is in series. That is resistors parallel, inductors parallel concept is similar to capacitor series. But capacitors parallel is similar to resistors inductor series concept. Only capacitors is different. V by, because why it is a difference, sir? Because impedance is inversely proportional. For capacitor, impedance is inversely proportional. That's the reason why we are getting different. V by equal to R1 R2 by R1 plus R2. That is R equivalent. Okay, this is the equivalent resistance. That is R equivalent equal to, in parallel connection of two resistors, R1 R2 by R1 plus R2. This R equivalent equal to R1 R2 by R1 plus R2. Now we have to apply current division rule. If you apply current division rule, what is I equal to? I1 equal to V by R1. I1 equal to V by R. That is, what is the current through R1? You have to calculate what the current through R2 you have to calculate. That is I1 equal to V by R1. Shall I write like this? V equal to, from this, what is the observation? V equal to I into R equivalent. From this, what is V equal to, friends? You bring this I this side, V equal to I into R equivalent. That I am writing. V equal to I into R equivalent by R1. What is R equivalent? R1 R2 by R1 plus R by R1. This R1 R1 cancel. What is I1 equal to? What is I1 equal to? V into R2 by R1. I told already, the series connection, parallel connection of resistor is similar to series connection of capacitors. I equal to V into R2 by R1 plus R. That is, if you have to calculate what is the current through this R1, take this resistance. Sorry, 1 minute. This is not V, na? It is I. This is not V. This is I, na? This is I, na? Yeah. If you have to calculate what is I1, take the total current. If you have to calculate I1, take opposite resistance. Opposite to this one is R2. That is I into R2 by R1 plus R. Similarly, I'm writing here. That is, what is I we got? What is I1 we got, friends? This I1 equal to, better to write in the next slide. What is I1 you got? This I1 equal to I into R2 by I1 equal to I into R2 by R1 plus R. Similarly, directly I'm writing, again no need of derivation. Can you tell what is I2? Total current into, if you want to, opposite resistance is R1, R1 plus R. These two rules are called current division rule. This is called current division. This is called a current division rule. Parallel connection, current division rule. Series connection, voltage division rule. Because in series connection, voltage is divided. In parallel connection, current is divided. Current division. Next, if two equal resistors are connected in parallel, if two equal resistors are connected in parallel, if two equal resistors are connected in parallel, then what is R equivalent? That is R1 R2 by R1 plus R2. No? That is R into R by R plus R. This is equal to R by 2. Similar to capacitor series connection concept. Okay. This is for two equal resistors. Now, if n resistors are connected in parallel, like this, you have to write if n resistors are connected in parallel. If n resistors are connected in parallel, if n resistors are connected in parallel, then how you can write? That is, first draw this. That this is R1 resistor, this is R2 resistor, and so on. Rn resistor. This is R1, this is R2. Let the current through R1 is I1, current through R2 is I2, current through Rn is In. This is In. Okay. Let this total current is I. This voltage is V. Like this, n resistors are connected in parallel. 1 by R equivalent, no need of derivation, directly right? 1 by R equivalent equals 1 by R1 plus 1 by R2 plus and so on. This is 1 by R1 plus 1 by R2, 1 by R equivalent. This is equal to 1 by R equivalent. This is, I'm writing like this. If you want one more step here, this is I by V. This is I by V. Okay, this I'm writing here. This 1 by V by I, you bring this side. 1 by R1 plus 1 by R. Then 1 by R equivalent. 1 by R1 plus 1 by R. Clear? I by V, V by. What is V by here? V by equal to R equivalent. V by equal to R equivalent. This is the reason. That's why 1 by R equivalent equal to 1 by R1 plus 1 by R2 plus and so on. Any number of resistors. Now in this case, if you have to calculate current division rule, how to apply current through nth resistor? How to apply current? I told already, the concept of resistors in parallel is similar to concept of capacitors in series. Then you have to apply like this: I into 1 by R. 1 by Cn I apply now. 1 by Rn by 1 by R1 plus 1 by R2 plus some. If you want, clearly I'm writing current through nth resistor in current division rule. If two resistors are there, easily you can apply like this. If more number of, this is important. If more number of resistors are given, how to apply? I into 1 by Rn. I into 1 by Rn by, yes, clearly I'm writing I into 1 by Rn by 1 by R1 plus 1 by R2 plus and so on. This is in current through nth resistor. We can also write in terms of conductance. In equal to 1 by resistance is nothing but a conductance. I into Gn, G1 plus G2 plus and so on. What is 1 by resistance, friends? 1 by resistance is nothing but a conductance. If you have to take conductance, In equal to I into G. If you have to take resistance, I into 1 by R. See the concept, friends. If two resistors are there, how to apply current division rule? Simply that total current into opposite resistance by total resistance. Total current in I2 if you want, opposite resistance. If more number of resistors are there, go for this formula. I into 1 by Rn by 1 by R1 plus 1 by R2 plus and so on. Similar to capacitor in series. If n equal resistors are connected in parallel, if n equal resistors are connected in parallel, if n equal resistors are connected in parallel, then what you have to take? That is R equivalent equal to R by N. Two equal resistors R by 2. Na? N equal resistance is R. Next. What is the parallel connection of inductors? Parallel connection of inductors. Actually, to explain this parallel connection of inductors, you have to consider the impedance. To explain the parallel connection of inductors, to explain the parallel connection of capacitors, you have to take the impedance. Yes. Yes. First, I am drawing the impedance. Let's consider impedances first. Let two impedances are connected in parallel. This is Z1. This is Z. This is Z. First, I am writing parallel connection of inductors and parallel connection of capacitors. And parallel connection of capacitors. Parallel connection of capacitors. Let's consider impedances. Let's consider impedances. Let two impedances are in parallel. This is Z1 and this is Z2. Let this voltage is V. This current is I. This is I1. This is. We know that in parallel connection, voltages are equal, currents are divided. VZ1 equal to VZ2 equal to V. Voltage across Z1 equal to voltage across Z2 equal to. So what is I equal to? I1 plus I. I equal to I1 plus I. Shall I write like this? This I equal to, what is I1? V by Z1 plus V by Z. Take V is common. I by V equal to 1 by Z1 plus 1 by Z. Then you bring this I into the denominator. 1 by Vi equal to 1 by Z1 plus 1 by Z. Shall I write like this? 1 by Z equivalent equal to 1 by Z1 plus 1 by Z. Then 1 by Z equivalent equal to Z1 plus Z2 by Z1 into Z. If you have to calculate Z equivalent, Z1 Z2 by Z1. Similar to resistance. Z1 Z2 by Z1 plus Z. This is for impedances. What is the Z equivalent here? Where Z equivalent equal to V by I. That is, what is V equal to I in? What is Z equivalent equal to V by I squared. V by I. That is Z equivalent equal to V by I. From this V equal to I into Z. V equal to I into Z. Clear? Okay, this Z equivalent equal to Z1 Z2 by Z1 by Z. Now I have to calculate I1. What is I1 equal to V by Z? Current division rule. I1 equal to V by Z. V equal to I into Z equivalent. Then what is Z equivalent? Z1 Z2 by Z1 plus Z. By Z1 Z1 cancel. I into Z2 by Z1 plus Z. Similar to resistors. I into Z2 by Z. But inductor and capacitors will be different. And I1 equal to I into Z2 by Z1 plus Z. This is called current division rule. Similarly, I2 equal to steps. I into Z1 plus Z. This you have to consider. With this knowledge, now this concept I am explaining for which one? Inductors and capacitors. For inductors. That is series connection of inductors. Series connection of inductors. If we take the series connection of inductors, that is let's consider, sorry, not series, parallel connection. I am explaining parallel connection. Sorry, parallel connection of inductors. If you consider the parallel connection of inductors, that this is L1, this is L2, this plus minus, that this is I1, this is I2. If inductors are in parallel, we know that Z equal to J omega L. Then what is the Z equivalent? Z equivalent equal to Z1 Z2 by Z1 plus Z. Then J omega L equivalent equal to J omega L1 into J omega L2 by J omega L1 plus J omega L. That is L equivalent equal to, by simplifying this, L1 L2 by L1 plus. Similar to resistors. L equivalent equal to L1 L2 by L1 plus. Then what is I1? Directly how to I1 equals to I into Z2 by Z1 plus Z2. That is I into J omega L2 by J omega L1 plus J omega L. Then I into L2 by L. Similar to resistors. Then if you want I1 equal to I into opposite inductance by total inductance. Current through L1 is that opposite inductance by total inductance. Similarly, what is I2? Similarly, I2 equal to I into L1 by L1 plus L. L1 by L1 plus L. If two equal inductors are in parallel, that is L equivalent equal to L by 2. If n inductors are in parallel, similar to inductors concept is similar to resistors. That is 1 by L equivalent equal to 1 by L1 plus 1 by L2 plus and so on. If you have to calculate current through nth inductor, then I into 1 by Ln by 1 by L1 plus 1 by L2 plus similar to resistors in parallel. Then if n equal inductors are parallel, if n equal inductors are parallel, inductors are parallel. If n equal inductors are parallel, L equivalent equal to L by N. Parallel. L equivalent equal to L by N. Clear? Well, inductors are parallel, L equivalent equal to L by N. Next, capacitors. Capacitors in parallel connection. Capacitors in parallel connection. Capacitors in parallel connection. Yes. In capacitors in parallel connection, let's consider two capacitors are connected in parallel. Let this is C1, this is C2. Let this is I. This is I1, this is I2. Let this is V strips. How take the impedance? Z equal to 1 by J omega. Then what is the Z equivalent? Z1, Z2 by Z1 plus Z2. What is the Z equivalent? 1 by J omega C equivalent. 1 by J omega C1. 1 by J omega C. 1 by J omega C1. 1 by J omega C. If we simplify this one, then 1 by C equivalent equal to 1 by C1 into 1 by C2 by 1 by C1 plus 1 by C. Then you simplify this one, students. What you can get? That is 1 by C1 plus C2 you can get. Then from this, what is the C equivalent? C1 plus. That is capacitors parallel is similar to resistor series. Capacitors parallel combination is similar to resistor series. Capacitor series connection is similar to resistors parallel concept. This is only different, students. Only capacitors formulas are resistor inductor is same analysis. But capacitors is parallel is similar to resistor series. Capacitor series is similar to resistors parallel. That point of view, C equivalent equals C1 plus C2. Then similarly, how to apply like this? What is I1? I1. Again, no need of derivation directly. Resistors parallel is similar to that is similar to resistor C. Sorry, capacitors parallel is similar to resistor series. Now that's why we have to take same capacitor C1 plus C2. Take same capacitors. Resistor is different capacitor. Resistor. If it's a resistor, you take an R2. If it's a capacitor C. What is I2, students? I into C2 by C1. This is important. If n equal capacitors are if two equal capacitors are series, if two equal capacitors are series, what do you have to take? If two equal capacitors are series, so parallel. Two equal capacitors are parallel, not series. Series are already completed, are parallel. If two equal capacitors are parallel, what is C equivalent? 2C, similar to resistors. C equivalent equal to 2C. Next, if n capacitors are parallel, if n capacitors are parallel, if n capacitors are parallel, 1 by C equivalent, sorry, parallel connection, similar to series connection of resistors. C equivalent equal to C1 plus C2. If n equal capacitors are parallel, if you have to calculate what the current through nth capacitor, similar to I into Cn by C1 plus C2 plus, similar to resistors. I where V into Rn, here I into Cn by C1 plus C2 plus and so on. I into Cn by C1 plus. If n equal capacitors are parallel, if n equal capacitors are parallel, capacitors are parallel. If n equal capacitors are parallel, then we have to write what you can write. If n equal capacitors are parallel, what is the equivalent equal to NC? C equivalent. This is the concept of series parallel connection of resistors in series and parallel. What is the analysis? Inductor series connection, parallel connection, capacitors series connection and parallel connection. Once again, I'm repeating. Series connection of resistors, inductors concept is same. But series connection of capacitors is similar to analysis is parallel connection of capacitors. So parallel connection of resistors. Parallel connection of capacitors is similar to series connection of resistors. That observation is very important. Yes, friends, here final conclusion observation I'm giving. This is the note point. In series connection, series connection for resistors, for resistors, for resistors, R equivalent equal to R1 plus R2 plus also. V1 equal to V into R1 by R1 plus R2. V2 equal to V into R2 by R1 plus R2. If you want to calculate Vn equal to V into Rn by R1 plus R2. This formula is mainly R equivalent equal to two equal resistors, R plus R, that is 2R. R equivalent equal to N equal resistor, R plus and so on, N resistors, that equal to N. For inductors, that is L equivalent equal to L1 plus L2 plus and so on. L equal two equal inductors, L plus L, that is 2L. N equal inductors, L plus and so on, N inductors. This is equal to NL. That is V1 equal to V into L1 by L1 plus L. Voltage divided. V2 equal to V into L2 by L1 plus L. Vn equal to nth V into Ln by L. This is for series connection. For capacitors, then 1 by C equivalent equal to 1 by C1 plus 1 by C2 plus and so on. Two equal capacitances are in parallel. So in series, 1 by C plus 1 by C, that is 2 by C, that is C by 2, that is C equivalent equal to C by 2. C by 2. That is C equivalent equal to C by 2. Then N, that is L equivalent equal to C equivalent equal to, if N equal capacitances are series, C equivalent equal to C by N. This formula you have for capacitor related formulas. Adding slide just. Then if you have to calculate what is V1 in capacitors, V into C2 by C1 plus C2. V2 equal to V into C1 by C1 plus C2. If you have to calculate nth voltage across nth capacitor, V into 1 by Cn by 1 by C1. This is important for everybody know for two capacitors. If three capacitors, four capacitors are series, how to calculate the voltage? How to calculate the voltage? This is for series. Just summary I'm giving students. For parallel connection, which formulas mainly how to parallel connection? In parallel connection of resistors, 1 by R equivalent equal to 1 by R1 plus 1 by R2 plus and so on. Then R equivalent equal to R by 2. If two resistors, R by 2. If n resistors, R equivalent equal to R by n. What is I1? Current division rule. In parallel connection, we have to apply I into R2 by R1 plus R. Don't take same resistor, opposite resistor. What is I2? You take I into R1 by R1 plus R2. What is current through nth resistor? I into 1 by R. 1 by R1 plus 1 by R2 plus and so on. It's also equal to I into Gn, conductance, by G1 plus G2 plus and so on. This is the current rule. If you have to apply for inductors in parallel, then what is 1 by inductors in parallel? 1 by L equivalent equal to 1 by L1 plus 1 by L2 plus and so on. Two inductances L equivalent equal to L by 2. N inductances L equivalent equal to L by N. How to calculate I1? V into L1, V into L2, not L1. Similar to resistors. V into L2 by L1 plus L2. How to calculate I2? I2 equal to V into L1 by L1 plus L2. Have to calculate IN. IN equal to V into 1 by L, similar to resistors. 1 by L1 plus 1 by L2 plus and so on. But 1 by inductance, don't write conductance. Okay, that is wrong. For capacitors in parallel, this is different. For capacitors, what is the equivalent? C1 plus C2 plus and so on. Two capacitors are in parallel, C equivalent equal to C. N capacitors in parallel, NC. What is I1 equal to I into C1 by same capacitor? See the difference, friends. Just for quick revision, I am giving this summary. C1 plus C2. Capacitors parallelly similar to resistor series. C1 plus C2. Nth current to nth capacitor, IN equal to I into Cn by C1 plus C2 plus and so on. Yeah, this is about series connection of resistors, inductors, capacitors, parallel connection of resistors, inductors, and capacitors. With this knowledge, next I have to discuss what are the different types of sources. What are the direct source, alternating source, independent sources, dependent sources. What exactly different types of independent sources? What are the dependent sources? Independent sources, independent voltage source, ideal voltage source, practical voltage source, independent current source, ideal current source, practical current source. Then what are the different types of dependent sources? After explaining this, you have to see some practice questions. Then we go for the nodal analysis and mesh analysis. This is about the today's session. Thank you. Any doubt? Once again, please go through whatever I explained. I will share this PPT. Please go through the PPT steps. Who are not joined in Telegram channel, I already given smart gate rankers. You please join that one. You have to take this PPT. All are joined this Telegram. Still anybody not joined? You please note down. Smart gate rankers. If anybody not joined, this is a Telegram channel. Smart gate rankers. You have search in our Telegram channel. All are I think all are small letters only. Smart gate rankers. No space. Okay, thank you, students. Next session will take. I'm ending the session.